some trip from point A or internally. Extent of what this is, you've most likely used a similar service like this before, maybe without even realizing it, because most apps like Uber and Lyft use internally a service like Google Maps to kind of handle that coordination. Because these systems are so complicated, you wouldn't want every single application that needs some type of mapping or navigation to have to implement their own from scratch, so they use a service like Google Maps usually. And at its core, Google Maps is about being able to travel from point A to point B, whether you're going to be walking or driving. Most likely it's about navigating from one place on the earth to another place. Usually some trip will be maybe 30 minutes if it's a short drive or a walk, but maybe a few hours, like 4 hours, or it could even be a cross-country trip. But if that's the case, you probably won't get it done in a single day. But it's important that our service makes this route as short as possible. But maybe distance isn't the only thing. Maybe we want a short distance of 10 kilometers, but maybe a 15-kilometer journey is actually faster because this one has more traffic. Or maybe the longer route, we're able to take the highway so we can drive faster. And of course, we'll be using a phone to actually handle this. We're probably not going to bring our entire computer, though we could, but most commonly a phone is what we'll be using. And this phone will support a GPS so that we do have our location tracked and we can dynamically update the route as we get closer to our destination. And one other thing that I think is worth mentioning is this concept of geocoding, which we kind of humans think in terms of physical addresses. Google's address is something like 1600 amphibian, something like that. I don't remember, but some physical address like this that will actually be mapped somewhere on the globe, which is a sphere, as we know. And we kind of think of coordinates on this sphere in terms of longitude and latitude. And this kind of makes up our coordinate system. You can think of the longitude being some type of decimal, let's say 101 point something something, and similar as the latitude. And these two values will correspond to some position on our grid, which is a sphere. But I'm going over this because, as we'll see, when a user wants to navigate somewhere, they're going to give some source, which is the starting position, which is an address, and then some destination, which is also an address. But we know that we can actually convert those into integers, which we're going to be using internally. So now let's start with the functional requirements. There's a lot of complexity with Google Maps, so we're going to keep things simple. We want to be able to navigate from a source to a destination that is user specified, and this should give us a reasonably good route. It doesn't necessarily have to be the fastest, but based on the traffic information we have, we should try our best to find the fastest route that we can. We should track the user's location because, of course, as the user is looking at their route on their phone, they should see updates in real time, ideally. So as they get closer to their destination, they're on their phone, the map route should reflect that. And we should be able to give an ETA, which is expected time of arrival, basically an estimate from our side using the traffic data that we have available. And most importantly, we are going to assume that we already have the map data. We don't actually have to build that. We assume that we already have that map data, and it's something on the order of terabytes, let's say, maybe 5 terabytes. And this kind of gives us all the data of the roads and how they're connected together and all of the physical addresses on the earth. And moving on to non-functional requirements, we are going to assume that we are dealing with a pretty massive scale. I think Google Maps has about 1 billion daily active users. So we are dealing with scale, but I think the most important thing is accuracy. We definitely don't want to give an incorrect route, but assuming that we already have the map data, that's not really going to be the problem. Of course, we want to have as good availability and reliability as possible, but there's something super unique about these non-functional requirements. I think one thing is that latency is somewhat tolerated when it comes to generating the route. It's okay if it takes us a few seconds to generate the route, because ultimately after the user gives the source and destination, it's not like they're going to immediately start driving 1 second later. If they have to wait 5 seconds, are they even going to notice? Probably not. But when it comes to real-time updates, updating the user's location, we probably want that to be fast, at least if they're traveling pretty quickly. Because as you're driving, you want to hear the voice assistant say, turn right in 500 kilometers. Well, 500 kilometers is a pretty long distance, but you get the idea. You'd want to know before you missed the turn. But the good thing is we don't have to worry about the latency in that case, because user location updates, at least client side, is something that we want to have low latency. So now let's go over the high level design. But the first thing I want want to talk about is this concept of spatial indexing. It's about querying spatial areas like maps as quickly as possible. Now, to oversimplify things, let's think of it with an XY coordinate system, which we are more used to than longitude, latitude most likely, but the idea is the same, even though this is a two-dimensional grid and we know that the Earth is three-dimensional, but the surface is two-dimensional, so we're going to think of it in this terms. What would happen if we tried to store this spatial data, like this is a map and we kind of break it up into little pieces? What would happen if we tried to store this in a relational database or even a non-relational database? Well, we would want to query still based on some key. Well, we could index based on the coordinates, right? Like, let's say this is the map data, this is the map of the world, we could index it based on the X and Y coordinates. But what exactly does that mean? Like, if I give you a exact XY coordinate, let's say it's 100 and 50 is the Y coordinate, so this is my coordinate and this corresponds to some spot. This is 100 and this is 50 and we get to this position. Well, that's just one point. So what exactly does that even mean for us? When we are looking for a route, we want a little piece of the world. We don't just care about a single point, we care about 2 points and we care about connecting them together. And if we give a very, very precise point, most likely it's not going to be this simple. A longitude, latitude could go out to multiple decimal places, like 1.123, and this could be 0.456, something like that. So are we going to store an exact point for every single decimal place? We don't need to do that. So one concept when dealing with spatial areas and maps is to break up the entire space into these so-called tiles, which at their core are just breaking it up into squares. Why do we choose squares? Well, what would happen if we didn't do that? What would happen if we chose long, skinny rectangles? Well, that technically works, but most likely when you're at a position, you think of things in a, let's say, 1 mile radius. You may want to travel within that 1 mile radius. So it's kind of like a circle, but it's a bit complicated to break up this space with circles. So to estimate that, we'd use squares. And the good thing about using squares is we can do it recursively, which is even better than using these rectangles. Not many areas are shaped like a long, skinny rectangle. And when we start to think of things in terms of squares, it gets a bit better. We can break this up recursively, actually. So if this was the entire world, now we have 4 quadrants, and we can break up each of these as well. So this top right could be divided into 4 portions like this, and then each of those portions could get broken down further and further until maybe each of these little squares is just a 1 by 1 mile or 1 by 1 kilometer square. And this is a pretty common indexing technique that's used. It's used in data structures like quad trees, and it's also used in something called geohashing, which conceptually is very similar to a quad tree. Geohashing here would basically mean each of these quadrants has a label. So maybe this one is 0, 0, this one is 0, 1, this one is 1, 0, and this one is 1, 1. So that's the label. But when we take, let's say, this portion and then start to subdivide it into 4 more pieces, each of them starts with a 0, 0. It's kind of like a decision tree. It could look something like this, where this 0, 0 corresponds to this 0, 1 corresponds to this, and this and this. But then when we take this and subdivide it into 4 more pieces, then we pretty much do the exact same thing that we just did with this layer. So we would have 0, 0, 0, 0. These 2 zeros would mean it's this area, and this one, we're kind of running out of space here, but hopefully you get the idea here. We would have 0, 0, 0, 1. This 0, 1 corresponds to this, and then this one would be 0, 0, 1, 0, which corresponds to this, and then we'd have 0, 0, 1, 1, which means bottom right. And we could keep recursively subdividing this. As you can see, this conceptually is pretty similar to a quad tree, but the good thing about geohashing is you actually don't need a data structure. You can just do an algorithm. So conceptually, we are given some physical address, and assuming we have a way to map physical addresses to, you're probably using their GPS coordinate, or if we have like a source and destination physical address, we could have some mapping with that to the longitude, latitude, and then using that longitude, latitude, which could be a very, very specific point. It could be one little point in this quadrant, and we're not necessarily storing every single decimal place in a database or data storage solution, and not that we would need to anyway. If we're storing a map, we probably want not just that point, but we want all that area around the person. So we would use a spatial index like a quad tree or maybe geohashing to very quickly find all of the information. Here, this quadrant is actually a map because that's how you can imagine routes are stored. Like 2 cities could be represented as nodes, and then we have have a bunch of nodes in between them, and this is kind of a graph. So we might be storing a graph database, for example, but to index that graph and to index the portions of that graph, we are using a spatial index like a quad tree or geohashing. And so when we use the longitude latitude of a user to query our database, we get a square with maybe a 1 by 1 kilometer radius, and that will give us all the nearby roads for the person. And assuming they gave us a source and a destination, and maybe their source starts over here, but their destination is somewhere over here, and we want to find the shortest path between these, we would run a graph algorithm like shortest path Dijkstra's algorithm. Though that's kind of getting into the data structures and algorithm space, we would conceptually start here somewhere and run Dijkstra's, but we don't need to load the entire map of the entire Earth into memory to run that algorithm. So what we would probably do is just have this tile, and Dijkstra's is based on breadth first search, so we'd go in all directions, and then from this one tile we'd want to look at the neighboring tiles until we eventually get the shortest path, whatever is the first path that reaches our destination. That would be what we return to the user. So you can imagine that spatial indexing is going to make this faster just because of the nature of the data that we're storing. It's not exactly relational data. It's not like we're doing a bunch of complex joins or anything like that. So spatial indexing is one very key component of being able to find these tiles quickly, and then to traverse the tiles themselves will probably store a graph-based database. At least that's one possible solution. And I also think it's worth mentioning that spatial indexing is actually something that's supported. The exact implementation can vary, but it's actually supported by many database management systems, both cloud-based databases, things like DynamoDB, as well as open source databases like Postgres, and it's something that's pretty common. That's what I'm trying to get at. So now let's get into the high-level design. We actually have two services here. One is the route service, which is what's first going to be used to actually generate the fastest route, which could be either the shortest route or it could be the shortest route taking traffic into account. But the ultimate thing is that this will return a route to the user, which will then display on their device and that they can then use. And this is really the core functionality of Google Maps. This is the most important thing because you don't really need to dynamically update the user's location, because you don't actually need a location service, though we are going to be tracking the user, and we're actually mainly going to be using this data for traffic information, so that if we have 1 billion users, that will give us quite a lot of information on which roads have a lot of traffic at a certain point in time, and we can use historical data as well. But Google Maps actually has an offline mode. You may or may not have used it, but basically once you have that route, you don't need an internet connection. You just need the GPS in your phone, and that will tell you where you are in terms of your route, like how close you are from your destination, and that will actually be sufficient. So that's what we're going to mainly be focusing on, the route service. And let's assume that our route service is able to hit the graph database, and remember, we already have all of the route data there, so we don't have to worry about generating that. We're just choosing to store it in a graph database because that is one efficient way to store it to be able to determine shortest paths. And this caching layer in between isn't super important, but there might be some common routes between major cities, major metro areas, so maybe that will make it faster to generate certain routes or maybe portions of certain routes, but this isn't really the key component in this design. And one way that we can actually shard this database is maybe based on the first few digits of a geohash, for example, because we just need similar close together tiles grouped together in a shard. So if all of the tiles for this quadrant were on the same shard, that would be fine. We don't need this little tile over here and this tile to be in the same shard. If we really need to generate a super long route like that, that probably won't be the biggest deal. If it takes 20 seconds to generate this type of route, wouldn't be the end of the world if you're traveling, from one country to another. Most likely you would just take a flight for that anyway. You probably wouldn't need Google Maps. But alternatively, each tile could have all the route information, and we could actually store all the information for each tile in a NoSQL database like a document store. And each tile wouldn't have to be small enough so that it could be stored in a document, but then each tile will reference all of its neighboring tiles so that we can group them together. And the way we would be able to index that, possibly we could use an in-memory quad tree, and that quad tree could be stored in a caching layer. Well, we wouldn't probably call it a caching layer, but we'd definitely store it in memory, because the size of that quad tree isn't really the major data that we're storing, because the routes themselves are going to be stored in the NoSQL database. So that's kind of an alternative, but I think a graph database here makes enough sense. Oh, and I forgot to mention that the quad tree would only help us in searching for the key of every single tile. Once we have that key, just use it as like a hash map key in the NoSQL NoSQL database. When you have a key, you can instantly find the document, assuming that we're using something like DynamoDB, which is sort of a document database and a key value store. Now let's take a look at our location service. So all of the location data is also going to need to be written to storage, but we don't need to write it to our graph database. We're actually going to have a separate store for this, and most likely we would use a NoSQL database, something that can handle a lot of writes like time series data, because that's kind of what this is. So a common solution for a problem like this is to use something like Cassandra, which can be optimized for heavy writes. So we'll be able to have historical data on which roads have how much traffic at each point in time, like each day, each hour, stuff like that will possibly be helpful for our route service to not only find the shortest route, but also be able to find the fastest route based on the amount of traffic. But because of the massive amount of data that we're going to be writing here, we would not directly read from this. We'd probably have a caching layer in between, and we probably wouldn't even want to actually read the data here itself. We would probably want to take the location data maybe in real time, that would be ideal, and then have some type of stream processing in between. And at a high level, we could have a message queue, something like stream processing. Kafka would be pretty helpful. I think with AWS, they have something similar, which is called AWS Kinesis. But basically, we would be feeding the data into another data store solution, and likely we'd be doing some processing in between. But basically, we would aggregate the traffic data in some storage solution so that our routing service not only has the route information and is able to determine the shortest path based on the graph, but also based on the traffic. So at a high level, you can think of the routing service is getting the graph, which could look something like this: a network of nodes. And initially, we just have some weights here, which tell us the distance, but taking the traffic data into account, maybe the weights of every single edge actually change. Maybe there's a lot of traffic here, so we bump this up to a 6, but there's less traffic here, so this is now a 3, and maybe this is the overall route, so this is 9, this is 8. So if we're trying to travel from here to here, maybe now we would take this route, but if there's less traffic, maybe this is actually a 4, so then we'd want to take this route. That's at least at a high level. You can see why traffic information would augment our graph, which would augment the shortest path. So now let's go into the details, even though we kind of already discussed many of them. One thing worth mentioning is the location data of every user. What would the schema of something like that look like? Well, we'd want to have the user ID, and periodically, maybe every few seconds, we'd want to send the location update of the user as they are moving. Maybe if they're stationary, we can somehow detect that on the client side and not send any data, or maybe we still choose to. Maybe that tells us that they are stuck in traffic. So we'd send the user ID, we'd send the timestamp, of course, because that's relevant. That kind of tells us how fast they're moving as well, and we'd send the longitude, latitude, but basically their location data, which we can maybe intelligently do something with that. We can encode that into some type of index for fast retrieval. Now, if we want to send real-time updates, we can use polling every few seconds. We can send a request from the client to the location service, or maybe a better thing would be to have WebSockets here for real-time updates. And we can also listen possibly for real-time updates to maybe traffic conditions have changed and there's a faster route for us. Maybe the routing service could intelligently determine that. Maybe we'd have another service separate from the route service, because this is used to actually generate a route. Maybe the location service could actually send information back, which is very much possible with WebSockets. Now, I want to think about this high-level design and then point something out to you. Let's say we give a source and a destination to the route service. We generate a route. It happens to be the fastest route based on traffic conditions. But what exactly are we going to be doing with a route? This is basically the instructions, every turn that we have to take, every freeway exit and stuff like that to get to our destination. But assuming we're going on something like a 1-hour drive, the instructions themselves don't really give us a picture, do they? When I say picture, I mean like the actual map itself. When you're going on a drive, you have that map in front of you, and you're probably using it, though sometimes maybe you just listen to the voice instructions. Maybe that's good enough for you, but we probably want to be able to support this. So when we think about tiles, we don't just mean the routes themselves, but we actually have a picture of the map. But where is that picture going to be rendered? Where is it going to be generated? And does it even need to be generated? Because, I mean, isn't that the whole point of a map, that it's static? Or if it does change, it obviously is going to change for everybody. So this static map is also going to be a picture. So it's image data. So that kind of tells me that maybe we can can use a content delivery network to store this image. And not just one image, actually, we're probably going to be having many images. If we just had a single image for the entire world and we sent it back to the user, that would be a very, very large image. So we definitely don't want to do that. We are going to break it up into pieces. We can do it the same way we did with spatial indexing. So to actually fetch those images, the user will make a request to the CDN, which is actually pulling images from an object store. It makes sense to have a CDN because users in a certain area of the world are going to be using maps from that area. They're going to be needing routes for that area, and most likely this. So that encoding is not built by the CDN, but maybe it's fetched from the route service or a different service, and that's what allows the user to know how, or at least allows the user's device to know which request to make to fetch the correct tile image, and then that image can be rendered on the user's device. And it's still okay. The CDN still does speed things up for us because the route service will not really have to send much data back. It may have to make a query to a quad tree, or maybe we'll have to run geohashing, but the data itself that it sends back to the user will be a small amount of data. But when the user makes a request to the CDN, it will be sent an image back, which, and in terms of scalability, we kind of omitted the fact that we'll be having load balancers in between all of these services, and a bit on how we would scale the NoSQL database, for example, and the traffic data. But we definitely covered the big picture. We could have gone a lot deeper into a lot of the domain knowledge areas, which I think isn't super useful for system design because that's not really what it's about. It's about being able to use building blocks to come up with a big picture solution. One thing that I do think is worth mentioning though, Uber, which obviously uses maps for a lot of their products, they have an interesting approach on spatial indexing. As you can see, they actually break things up recursively into hexagons, which you can imagine is a bit more complicated because it's not as simple obviously as a square, and recursively breaking it up can also get a bit more complicated, but they did this because it does improve the overall accuracy, and it makes sense because at the beginning we think of things in like a mile radius or a kilometer radius, but we think of things in terms of circles. That's a good way of thinking of things, but it's hard to break up spaces recursively into circles. That's why we use squares. But as you can see, a feasible solution is definitely possible with hexagons. You can check out this article on Uber's engineering blog for more details. Next, let's design a distributed key value store. So this is a bit different than what we've been doing so far. Instead of designing like an application or the high level, we're going to actually dig pretty deep into just one component, which in this case, by key value store, I basically mean a NoSQL database, at least one type of NoSQL database. But I think this is really important because we use databases a lot. They're usually one of the most important components of our system. So being able to understand the complexity that goes into them and what kind of trade-offs you can actually make just within a single component like a key value store is going to be helpful to see the big picture in a lot of the previous problems that we've designed. Now, to briefly go over the background, a database can be relational, which is typically SQL databases. NoSQL databases, though, are a lot more flexible. There's a lot of things that can go into this. Of course, there can be graph databases, there can be document databases like MongoDB, there can be more traditional key value stores like the original Dynamo, not DynamoDB, but just Dynamo. I consider DynamoDB to be kind of a hybrid between document databases and key value stores. There can be wide column stores like Cassandra, which kind of also fits into the key value definition, at least at a high level, though there's a lot of complexity within Cassandra. We could even be talking about something like Zookeeper, which isn't a traditional database, but it's used for coordination. It's considered a key value store. We could even be talking about Redis, which is an in-memory key value store, but this can be flushed to disk, which in some ways does make it a database. But let's say we want to kind of focus on a more traditional document database or key value store like DynamoDB or even Cassandra. That's kind of the area that we're going to be exploring. We're not going to go too far into one individual database, so we're going to keep it open-ended enough, but we are going to dig into some details. And when it comes to the functional requirements, we're going to keep things simple, even though we're not actually going to be focusing on these operations, but we want to be able to support a get operation. Given some key, we should be able to get the value. We want to support put, where we are given a key, we want to map it to some value, whether it's a document or a list of values or something like that. And we also want to be able to support deleting an object from our key value store given a key. Now, the non-functional requirements are a bit more interesting, and they're not surprising either. We of course want this to be durable. That goes without saying if we're designing a database. Let's say we do not need to support ACID, and that kind of also goes with the fact that we're using NoSQL databases. So we do not need to have ACID properties. Well, we do need to have durability, of course, that's the D, but mainly consistency since it doesn't make too much sense in the context of NoSQL databases. We don't really have relations and foreign key constraints and things like that, so that is easy. But atomic transactions, we will not need to worry about those as well. And this one is probably the most interesting: isolation. Remember, with SQL databases, isolation means that if two transactions are happening at the same time, they will appear as if they happened in a particular order. So why that's important is we won't get conflicts with SQL databases. We can lock a value. Like if this transaction is going, that row that this transaction is running on may be locked, and then once this transaction is completed, then the next transaction can run on that same piece of data. So we will not run into conflicts, but with NoSQL databases, conflicts are a thing. And lastly, we need our database to be scalable. That is also a very important part of NoSQL databases. Generally, scale is one of the big important things, so you can already kind of see that we're going to have to touch upon replication, which is a way to handle scale, and as well as sharding, aka horizontal partitioning. Now let's get into the high-level design, which is going to be a bit different. I'm mainly just going to be covering what we are going to cover in the details, but this is generally what we should cover when we're talking about key value stores. And let me explain a little bit about this. First of all, how we are actually going to be storing and indexing data. We know with SQL databases, they generally use B trees or B plus trees, and even some NoSQL databases use this as well. But since we already briefly talked about these, I'm going to be covering another type of data indexing strategy that NoSQL databases sometimes use, an example being Cassandra, which uses LSM trees. We'll talk about that more in detail later, but this is basically a way to optimize for writes, for very quick writes, but not necessarily quick reads. And another thing that's very important to cover is replication. When we're talking about scaling our NoSQL database, we of course have to replicate data. We can't just hit a single node and expect to be able to store all of our data. But replication is not easy. There's a lot of problems that you run into. We are going to have to consider the CAP theorem, and even more than that when we are talking about our replication strategy. And again, when it comes to dealing with scale, not just high traffic, but maybe a large amount of data, we can't expect all of our data to be stored on a single machine. We might have to split it out and then maybe put half of our data on one node and then another half on another node. And so that's going to be horizontal partitioning. Don't forget about vertical partitioning, which is less powerful. Vertical partitioning is basically we actually keep all of our data on a single machine, but maybe our table, if we're thinking of things like with SQL, you have a table, but you actually split that table, not like this, where half that data gets sent to one machine and then half of it gets sent to another machine, but we actually split it like this, where that table itself gets a little bit smaller. That can make queries faster, and it's a bit easier than horizontal partitioning, but obviously it's less powerful. It's analogous to horizontal scaling and vertical scaling, where you can just take a single machine and then maybe add more resources to it. Yes, that's an easy thing to do, but there's limitations. With horizontal scaling, you can kind of infinitely scale things if you have a good strategy. So when we talk about horizontal partitioning, we are talking about sharding, and that's why horizontal partitioning is just a lot more common to be talked about than vertical partitioning, even though sharding is not easy to implement. But we will be kind of talking about some of the challenges that we'll run into. Also, we want to be able to cover what happens when a node fails, because of course we know that's going to happen. When you have many machines, you can't expect all of them to be running forever. If a machine goes down, we have to have a strategy for recovering and how our system is going to behave if something like that happens. And lastly, we talked about how if we don't have isolation with writes, then we may end up with some conflicts. So we have to have a way to resolve those conflicts and have our system be able to handle concurrent writes. So first, let's talk about how we're actually going to be storing and indexing our data. And we're going to be using a LSM tree, which stands for log structured merge tree. And this is used by databases like Cassandra, which can allow this to optimize for writes, for very quick writes. We'll see why that's the case. The biggest reason is that writes are batched in memory. What does that mean? Well, if we have a client, our client would most likely be a server, is sending requests to our database system. This is our entire database system. That write is actually not going to be immediately written to disk. That write is actually going to be written to memory in what is called a mem table. And periodically, as those writes are written to memory, eventually they're going to be flushed to disk in what is called an SS table. So first of all, you can see why on average, as let's say we write 100 records to our database system, and if all 100 of those go to memory, that's going to be pretty fast to write. And maybe after 100, our memory fills up and then we flush that to disk in a SS table. So you can see why this is one way to improve speed. But what is an SS table? Well, as we write data, this is a key value store, right? So every key is what's important. Every key is what identifies the data itself. So when we store that data, ideally we should be able to sort it based on the key value, because when we want to read data, we want to be able to find it within the SS table. So an SS table actually stands for sorted strings table, because it's sorted based on the key value of the data that we're storing. So when we search for it, we can do something like binary search. So that's what's going on at a high level. And I believe with Cassandra, the recommended SS table size is to keep it within the hundreds of megabytes, so maybe 100 megabyte or 200 megabytes, but to keep it that small. And we can additionally create more and more SS tables. It doesn't mean that our database is limited to 100 megabytes. That would of course be a problem, but we can have more SS tables, and ideally keeping them small. Maybe with the key value that we have, we'd be able to immediately check the entire range of values in this sorted strings table does not have the value that we're looking for, so we actually don't even need to run binary search on this one at all. We could look at the next SS table, something like that. Now that's what's going on with an LSM tree at a high level. That's why it's generally faster for writes, but reads actually can be a problem, because in the worst case we have to search through a bunch of SS tables. And possibly another problem that you might have identified, if we're initially writing to memory and then batching that and flushing it to disk, what happens if our system crashes? Then all the writes that were written to memory that weren't flushed, those would go away. And this problem is solved by taking every write and also writing it to a transaction log, but we won't go in depth on that. Now imagine if we want to actually update a value. If we want this to be write optimized, well, to update a value, you of course have to read that value first, right? So if we're trying to optimize this for writes, but not necessarily for reads, well, if we have to read the value anyway to update it, then that's kind of a problem. So how we can get around this with an LSM tree is actually, when we want to update data, we just create a new copy of that data. Well, not a copy of it, but we don't overwrite the existing data. The old value actually is still stored in some SS table somewhere, because we will have many of these. We may not need to find that value though. We'll just immediately write the new updated value to memory, and then eventually it'll be flushed to disk somewhere, maybe to a new SS table, and that old value still remains in the previous SS table. So you can see that this is another way to optimize for writes. But if we are storing old stale values, then that is going to continue to take up disk space. And even when you delete values, you don't actually overwrite the value in an SS table, because SS tables are immutable. No data can be deleted or overwritten. So if we wanted to delete a record, we would create a new value for it and then mark that value as deleted. So we'd say this key value, whatever it happens to be, something that is now marked for deletion. That means if we ever read that value, we will say that, well, this value shouldn't exist anymore. So that's what we're going to tell the client. The value doesn't exist, even though it probably is still stored somewhere on disk. This is called a tombstone, to delete something in this way without really deleting it. Now, I want to briefly mention that there are some optimization strategies where there is cleanup done, where the SS tables are merged and compacted, where if we have duplicate values, those duplicate values will be removed. If we have values that are deleted, those will also be removed. But we're probably getting a little too much into the weeds on this. But I do want to say that there are a bunch of other design decisions that went into this, and LSM trees are commonly used in NoSQL databases like Cassandra that we mentioned, as well as Google Bigtable, which Cassandra followed a lot of the design principles that Bigtable and of course AWS Dynamo kind of set out in their white papers. Next, let's talk about replication, because this not only provides us the ability to actually scale, but this also provides us some fault tolerance. If we have data that's replicated across multiple machines, we are less likely to lose all of that data, even if the machine was destroyed. And especially if we can replicate across multiple countries and multiple regions and zones, that would be even better for fault tolerance. But let's not forget that with replication, there can be problems, namely with data consistency. What happens if one replica does not have the most up-to-date data that was written to another replica? Well, to review, to better understand these problems, we have app theorem, which tells us that if there is a partition in the network, meaning that for some reason these two nodes are not able to communicate with each other. Originally, they are both up to date, but maybe one of the nodes gets written a new record where, let's say, with A is the key value, and the value itself is 1 originally, and this one has that as well, but now we change this one to a 10. Now this node has the 10, but for some reason this node can't copy that data over to the other node, so they become inconsistent, and if somebody were to read data from this node, they would not get the most up-to-date value. What we could choose to do at this point is say, well, this node should not be accepting any read requests, and that would basically lower our availability because not every node in our system is able to respond to requests. Or we could say, yes, allow this node to respond even though it's an inconsistent state, because we know eventually it will get written the most up-to-date value. This is the trade-off with app theorem. And additionally, with the extension pack else, even if there's not a partition between these nodes, if they are located somewhere else in the world, we know that to take any updates to this node and then send them to other nodes is going to take time. So maybe once that write comes in here, what we can say is don't allow this node to respond to requests until we've sent that data. And it might take, let's say, 50 milliseconds. So for 50 milliseconds, this node would not be available for reads, but we could do something different. So in this case, we are favoring consistency. That's the choice we have, even if there's not a partition in between these two nodes. But what we could also do is favor latency, which would allow us to immediately read from this node, and we don't have to wait an extra 50 milliseconds for that data to be copied. So in this case, we are lowering the latency to be as low as possible, even if we get an out-of-date stale value, because maybe 50 milliseconds later, we will get the most up-to-date value if we send another request after this value has been copied over here. So that's what this theorem states, that there is a trade-off between latency and consistency, even if there's not a partition in our network. And many databases, including Cassandra, choose to lower the latency. So that is kind of going after the eventual consistency model, which usually makes sense because we want our database to have low latency and to be able to handle as much traffic as possible. We don't want our nodes to not be available just because they don't have the most up-to-date value, though it does depend on what type of this value is, the lower the consistency of our system, because if we get a read from this replica or from this replica, we will not have the most up-to-date value. What happens if we go the opposite route and we set W equal to the number of nodes? Right now we have it set to the smallest value possible, which is 1. We can't really set it to 0. That wouldn't make a lot of sense in this context, but if we set this to 3, we're basically saying that data has to be written to every single replica before it's accepted. Now, the downside of this probably is going to be a value that is storing is going to end up going here to some external server on down. We have 2 instances. A has not sent a heartbeat in some predefined amount of time. Maybe that the threshold is 1 minute. After 1 minute, A has not sent a heartbeat. That means that A must have gone down. But it's not enough for a single node to be able to verify that A has gone down, because what if A isn't the node that went down? Maybe B has gone down. That's why it hasn't received a heartbeat, because B has been cut off from the entire network. So to detect nodes, do we really want every node to be communicated back up and when it way that other database systems use, which is more complicated? I believe the original Dynamo used something called vector clocks, which make things more complicated, but to use a similar concept of versions of the same value. A vector clock is basically a pair of values. So for a particular node, we have a version for every single value. So this pair corresponds to a single key. Like in our example, we were using A as the key, and then we had some value. This is not the value, but this is to say maybe we have 2 nodes here. This is node A, this is node B. So this would say that on node A, possibly we have a value of 1. So at least at a high level, instead of solution though, using these vector clocks, there's no simple way. Typically with Dynamo, the client was expected to handle the resolution. So there's not like a straightforward way. That's why for our design, I'm going to prefer the last write wins approach, because even though it's not perfect, it is more simple, and vector clocks are definitely a lot more abstract, though they are pretty interesting. But I think generally single key, like in our example, we were using A as the key, and then we had some value. This is not the value, but this is to say maybe we have 2 nodes here. This is node A, this is node B. So this would say that on node A, possibly we have a value of 1. So at least at a high level, instead of maintaining timestamps, we have versions. So on this node, node A, we could say that we have some value and it's version 1, and if we update that value on this node, we now have version 2 of that value, etc., etc. And maybe initially these replicas stay in sync, but maybe later at some point there is a new value that's written to this replica that's not written to the other replica at the same time, maybe. So on this node, maybe we have a value of version 1. These are different because they have a different node. Vector clocks can get pretty abstract, and the resolution though using these vector clocks, there's no simple way. Typically with Dynamo, the client was expected to handle the resolution, so there's not like a straightforward way. That's why for our design, I'm going to prefer the last right wins approach, because even though it's not perfect, it is more simple, and vector clocks are definitely a lot more abstract, though they are pretty interesting. But I think generally for most system design interviews, you won't be expected to go in depth into these. I did want to mention it though, because it's an interesting alternative. But that is generally what I wanted to cover. I know we talked about a lot of these concepts before, things like cap theorem and replication and consistent sharding, but we went a bit more in depth this time to get a holistic view on a lot of the things that can go into just as well possible. Next, let's design a distributed message queue. We've used message queues a few times throughout our designs, but we haven't really gone super deep into them, and they're a pretty important component, so I think it's worth understanding at a high level at least how they can be implemented and how we can scale them. First of all, the background with message queues, there's many different kinds, and there's been a lot of evolution over the years which has blurred kind of the differences between them. Talking about more of a traditional message queue, something like RabbitMQ, which started out as sort of a one-to-one mapping, so you produced messages on one side and then consumed them on the other side. So it was just one system creating messages, adding them to the queue, and then one consumer taking those messages. So kind of how a queue data structure works in code. Now I believe RabbitMQ actually supports more than just this, but I'm just kind of going through some of the basic history with message queues. This is a pretty straightforward pattern to understand, but then things get a bit more kind of complicated, but also a bit more powerful when you start talking about the pub sub pattern, which is also a pattern that can be applied to code. But in terms of distributed systems, they're also helpful and have additional complexity with them. At a high level, we have publishers and we have subscribers, as the pub sub name implies, but these are actually part of our application. So we could have some servers here, possibly they are payment transaction servers. Like every time we receive a payment, we have our application servers that do something with that payment information. Maybe these servers can't process the payments immediately, so we want to process them asynchronously, because if we can't handle the traffic of the payments, but we keep receiving payments, then eventually our servers might miss some of the payments, or we might crash and not be able to process them. We definitely don't want this to happen. If it takes a few extra seconds to process them asynchronously, that won't be the end of the world. Or maybe, so what we do instead is these servers, every time they receive a payment, we send them to our pub sub message queue system. These topics are sort of entities within the pub sub system. So first of all, the messages that we get will actually be persisted here. So in some type of persistent storage, they'll be stored so that we definitely will not lose them. And then eventually when the different servers, these are also part of our application, these are our subscribers that will be listening to these topics, and the messages from the topics will eventually end up with these subscribers, and these maybe will be the ones that actually process the payments, but the subscribers will get those messages as needed. If they can't process them all immediately, it's okay, because the messages can still be stored within the pub subsystem with topics. Maybe this topic is for payments, and maybe this topic is for something else. Maybe this is log data, or maybe some type of fraud detection system, and maybe we want both of these subscribers to actually get that fraud information. Basically, these could be different systems doing different things. One of them could receive messages from both topics, one of them will only receive messages from the topic it needs. So this also obviously adds some decoupling to our system, where the publishers don't need to know about the subscribers, they don't need to know how many subscribers exist. That kind of information is isolated within the pub subsystem. And of course, this also allows for additional scaling. So that was quite a bit on the background, but this gives us a good picture of what we're trying to accomplish here. And there's also other things that we kind of missed, in between the topics and the subscribers are actually another entity here called a subscription. We'll talk more about that later on. So now let's move on to the functional requirements. One of them being that we definitely want to support fan out. So with our distributed message queue, we want the same message to be able to be received by multiple subscribers, aka consumers. I want to kind of get the terminology out there as well. We talked about subscribers, but there's another term that's pretty much equivalent that's used called consumers. And when we talked about publishers, there's another term for it called producers. This type of terminology is much more commonly used with other types of message queues like Kafka. Kafka actually technically is not a message queue. It's more for event streaming, but the lines have sort of blurred between message queue and event streaming systems like Kafka. They really support a lot of the same functionality. Like Kafka does support fan out, it does support persistent storage. Messages can be retained in Kafka for a certain period of time, which brings me to the next functional requirement that we want, which is being able to retain messages, but in our case, we are going to simplify it and only retain the messages until they are delivered. And also, we want to support at least once delivery. But why that's important is because we want every single message that's received by our pub subsystem to definitely deliver that message at least once, because if we can't guarantee that, that means messages are going to be coming into our system and then some of them are never going to be leaving, aka some of those messages are going to be lost. And we definitely don't want that to happen. That's kind of one of the points behind using a message queue. There's other types of delivery with message queues, things like at most once delivery. Why that would be important is because we don't want the same message to be sent multiple times, because you don't want to end up with duplicate messages. With payments, that could be important because you don't want the same payment to be processed multiple times. So you want to guarantee at most once delivery. But if we have at most once delivery, but not at least once delivery, that brings us to a problem where the message might get dropped. So there's also a third type called exactly once delivery, which is, as the name implies, every message will be received and get sent out exactly once. We can guarantee that every message will be delivered exactly once, so we won't end up with duplicate messages and we won't end up with messages that get dropped. But we are not going to be supporting this just for simplicity. It's actually a pretty complicated problem to solve, and there's a lot of trade-offs that can be made when trying to design something like this. But for now, we're going to keep things simple and go with at least once delivery, because that's probably the most important. That's mainly it for functional requirements. Moving on to the non-functional requirements, there's nothing crazy that we want to support. Like, we don't need to get into the math, but of course this needs to be scalable. So ideally we should be able to horizontally scale our message queue. If we add more and more publishers and more subscribers, we should be able to scale out our system to be able to handle the traffic. And as we get more and more messages, we could have a lot of messages at the same time. We want to be able to scale that out as well. And we kind of already talked about this, but we do want persistent storage. We do not want the messages to be lost, and that kind of was already talked about with the functional requirements, but I still think it was worth mentioning here. And we talked about this with scalability, but we also want to be able to have high throughput. Okay, with that, let's get into the high level design now. So at a high level to review, remember the publishers are servers that our application owns, but they are not necessarily a part of like the message queue that we're designing. But of course, they're a very important part because the message queue doesn't really do anything if we don't have publishers and subscribers. Now, first of all, remember that publishers are going to be sending messages into the message queue, and then subscribers are going to be receiving messages from the message queue, and somewhere in between the messages are going to be stored to make sure that we never lose them. So at a high level, we know we're going to have some servers that are part of the message queue over here and another layer of servers down here, and we'll call these our publish forwarders, and these down here will be called the subscriber forwarders. This is not like a term that I've actually made up. This is actually a term that's used, but at a high level, the idea is simple. As publishers create messages, they will send the messages into our pub subsystem, and they'll be received by the publishing forwarders. Depending on the number of messages that we're sending and producing, we may need to scale the publish forwarders. But remember, the same message produced by this publisher might get sent to multiple subscribers. So it's important to be able to independently scale the subscriber forwarders, which will be sending the messages to subscribers. Maybe the same message needs to get sent to a bunch of subscribers. So we need to scale this more than we scale the publish forwarders. Or of course, we could have the opposite case where we have a bunch of publishers, but all the messages are getting sent to a single subscriber, and these ones don't even exist. Then we'd have like the opposite problem where we need to scale these more. And as those messages come into the publish forwarders, those messages will then be stored somewhere, possibly a database which stores all of the messages. And as soon as a message is stored by any of the publish forwarders, like just the journey of a single message, suppose this publisher sent a message and ended up hitting hitting this forwarder, then that message ended up being written to a database. As soon as it is persisted, we know that the message should never get lost at this point. So typically what's done is the PubSub system will then send a message back to that publisher telling it that the message you just sent me, maybe the message was 123, message 123 has been stored. Basically, one of the published forwarders, the same one, would send an acknowledgement, an ACK to the publisher. Your message has been stored. You don't have to worry about it anymore. You don't have to try to send it to me again, because if it never receives the acknowledgement, then the publisher definitely doesn't want the message to get lost. This is all part of the fault tolerance that the message queue should provide for us. But after the publisher receives the ACK, then it can send different messages if it has any. It can continue sending messages. Maybe different publishers will be sending messages, and generally this is done over HTTP. We won't really go into the security aspect of it, but probably we wouldn't want anybody to just be able to send a message into our system for obvious reasons. We wouldn't want them to, just throw a bunch of junk in there and maybe take our service down, maybe store too much data and things like that. But once those messages are stored, subscriber forwarders can read that data and then send it to their relevant subscribers. And then once a subscriber has seen a message, then they will actually send an acknowledgement back to the PubSub system. And once a particular message has been read by all of the subscribers, then we probably don't need to store that message anymore. If that message has been ACKed by every relevant subscriber, then we can probably remove that message from storage. This will ensure that we support at least once delivery, because if we guarantee that everyone has already seen the message, then we know we are safe to delete it, and we won't end up taking an infinite amount of storage. Now, to start digging into some of the details, which we kind of already did, the lines are kind of blurred between high level and details, but we might need a secondary data storage system, and this could be for metadata. Specifically, we might want to store information on how many subscribers we have. And before I actually get into that, I want to remind you that there is this concept of topics in a message queue, and we've kind of looked at this from the point of just a single topic. A topic is a way to organize messages. So when we get sent messages into our PubSub system, we may have a single topic for payments. For example, all payment information will get sent to this topic, and it makes sense that we would want to store messages of the same topic in a similar way. So if we ended up having a very large amount of messages, we'd probably want to shard this based on the topic if possible. But even a single topic may have too many messages. But also there is this concept of a subscription. So when messages are created and sent by publishers, they will go to a topic. They could go to multiple topics if the publisher decides that, but they will be organized based on a topic. Now, when messages are actually consumed and received by subscribers, they will go through a subscription. A subscription, one of the major things about it is that it's used to fan out information from a topic, to fan out the messages. So if we wanted, in this case, these two subscribers to receive messages from the payments topic, we could create two subscriptions for this same topic. So we have two subscriptions for that topic, and each of these subscribers, each of these servers listens to a single subscription. So this is a way to fan out the messages, and also this is a way to guarantee that each message is received by both of the subscriptions and both of the subscribers. Maybe one of these is to actually process the payment, and one of them is for fraud detection. We definitely don't want messages to only be received by one of them. We want both of them to receive it, and this is a way to do that. So these topics and subscriptions are sort of abstracted, but all that information will be stored in the metadata database. So we'll store which topics exist and which subscriptions exist, and this will allow us from this side, when a message has been acknowledged, we can go to our metadata database and see that a certain topic, the payments topic, it has two subscriptions on it, and we can record, okay, one of the subscriptions has already seen the message, but another subscription has not seen the message, it hasn't sent the acknowledgement yet. So then at that point we would know we can't delete that message yet, but maybe as soon as the other server sends the acknowledgement, then we see that both of the subscriptions on that topic have seen that particular message, so then we could go to our messages database and then remove that message. It doesn't need to be stored anymore because all of the relevant subscribers have already seen it. Now, ideally, we'd also want the messages to be first in, first out. So we ideally like to have ordering with the messages. So in the same order that messages are received from publishers and then stored into our system is the same order that we'd like to deliver the messages. So at a high level, the publishers can create some type of ID which is tied to the timestamp that those messages were received, and those messages can be stored in our database using that. Now, since we don't really need to do complex joins, we can probably just stick with a NoSQL database for storing the messages, because the message is typically like a JSON object anyway, but probably a relational database would work just as well here. A reason to go with a SQL database in this case would be for the ACID properties. In this case, if we possibly store the messages and just auto increment the ID, then we can kind of be sure that the messages will be stored in the order that they were received, and in that case, the isolation property of ACID would be important because we will be having multiple forwarders concurrently writing here, and we would want to write those messages in an isolated way. Now, there are other policies we can have for retention. We could design our system such that we can store messages even if every subscriber has received those messages. We could set like a certain policy, maybe a 7-day policy, even after every subscriber has acknowledged them, or we could set a 7-day policy where even if some subscribers have not acknowledged them, we will still delete the message anyway. So we can have some flexibility, and real message queue systems, including pub subs, and real message queue systems generally support this functionality. Now, another open question that remains is, what about replication of our messages? When we take a message and we just store it one time in a single database, and then we send the acknowledgement to the publisher, hey, we guarantee we are going to deliver this message, or at least it will never be lost. How can we make that guarantee if we're just storing it in a single database? What if this crashes? What if the data center explodes? Well, the data is definitely going to be lost. So probably we should replicate this among additional database instances. But how many times should we replicate it? Probably at least 3 is a good rule of thumb, especially if these 3 are located in different regions of the world. Another question remains, when should we send the acknowledgement to the publisher? If we take that message and we store it in just a single database, and we know we're eventually going to replicate it, but we might not. What if those other 2 crash or something happens? At what point can we safely tell the publisher we acknowledge that we received the message and it's been stored? Should we just sending the acknowledgement? Then we are lowering the latency, but that's also latency until it's been stored in 2 replicas, or should we wait until it's been stored in all 3 replicas? Because this is a trade-off between latency and fault tolerance. If we only store it in a single replica before sending the acknowledgement, then we are lowering the latency, but that's also not as good for fault tolerance because we have not stored it, we have not replicated that yet. So at some point the database could have crashed or been exploded or something, caught fire, and then we didn't replicate it, but we still sent the acknowledgement, so that's not good. Maybe we can wait, we can increase the latency, we can wait a little bit until that message has been stored at least 2 times. That's good for fault tolerance as well, because we know we replicated it in 2 different databases, or we could wait even longer on average until it's been replicated 3 times. So this is just a trade-off I think that's worth discussing. Depending on the throughput of our system and what we're trying to optimize for, we might be willing to be flexible on this number. Now, one last thing I wanted to talk about is pull versus push-based delivery. When these subscribers receive messages, we can do it 2 different ways. We can make it pull-based, which means that the subscriber will actually be pulling messages from our pub sub system. So the subscriber will be the one initiating the request. It will say, okay, I'm ready to process more messages. Let me make a request. Let's see if there's any messages ready. Well, one obvious downside is that what if there aren't any messages ready? Then this subscriber just made a request for no reason. And it doesn't even know when the next message will be ready. It could not be ready for hours. What's gonna happen in the meantime? Well, depending on the cadence dates that this subscriber makes requests on, the frequency, it could be maybe every 5 seconds it makes a request. That's going to be a lot of wasted requests. Or we could make it a lot slower. We could make it 30 seconds and then the subscriber will send a new request. The downside of this is that it may increase latency. There might be a new message here, but we won't see it for another 29 seconds because we have to wait. So obviously this is slower, but the benefit would be that the subscriber can actually process data when it sends the request. So this might be more suitable for batch-based processing. But push delivery, the message will be sent from the subscribing forwarder to the subscriber as soon as the message is ready. Now the downside here is that what if the subscriber is not ready? Well, that's fine. The subscriber forwarder will send the message. It will never receive an acknowledgement from the subscriber, so therefore maybe 10 seconds later it will try to resend the data. Now the downside here is that if it just keeps resending the message and this subscriber is not ready, that's also a lot of wasted time, and if too much data is sent, it could end up overloading the subscribers, though they'll probably never crash. It's just that they'll just keep getting sent messages and they can't really do anything with them until they're done processing the current messages that they're on. Now the good thing about this is it can minimize the latency. So if we're going for stream-based processing where we want the messages to be sent to the subscriber as soon as they're ready, this is the best thing. And generally it's not like you have to decide on one. Most message queue systems will support both pull and push-based message delivery. Now this is a high-level design of a message queue pub/sub-based system. It might be surprising to you how this system is actually not too different from the others that we've designed message delivery. Now latency, there might be a new message here, but we won't see it for another 29 seconds because we have to wait. So obviously this is slower, but the benefit would be that the subscriber can actually process data when it sends the request. So this might be more suitable for batch-based processing. But push delivery, the message will be sent from the subscribing forwarder to the subscriber as soon as the message is ready. Now the downside here is that what if the subscriber is not ready? Well, that's fine. The subscriber forwarder will send the message. It will never receive an acknowledgement from the subscriber, so therefore maybe 10 seconds later it will try to resend the data. Now the downside here is that if it just keeps resending the message and this subscriber is not ready, that's also a lot of wasted time, and if too much data is sent, it could end up overloading the subscribers, though they'll probably never crash. It's just that they'll just keep getting sent messages and they can't really do anything with them until they're done processing the current messages that they're on. Now the good thing about this is it can minimize, like you have to decide on. It might be surprising to you how this system is actually not too different from the others that we've designed. If we have persistent data, probably a blurring messages and something, like I said, is kind of being blurred between Kafka and just traditional. I think it's worth mentioning that Kafka, which is an event processing message queue, it ends up storing messages in something called a write-ahead log. So if you're interested in that, you can probably read up on Kafka. I think actually the correct term for Kafka is message broker, but the line, like I said, is kind of being blurred between Kafka and just traditional message queues. Also, I want to mention that in between these publishers and our pub subsystem, there will be generally a load balancer because these publishers could be located all around the world and we might want to load balance them in here. And for us to use like a really highly available key value source coordinator service to actually manage that, like manage the state of the subscribing forwarders, the coordination between assigning subscribers and forwarders, and manage the update, kind of just touched upon, things can get a lot more complicated, especially as you try to scale up and accomplish different things. Kafka is a very, very powerful modern message broker.